Let's see the applications of operational amplifiers. So in that we are going to see log and anti-lag amplifier. So first, log and anti-lag generally log and anti-lag amplifier, it is used to do the mathematical function log and anti-log. Logarithmic amplifier is used to compress the dynamic range of the signal. Let's see first logarithmic amplifier. It is a circuit of logarithmic amplifier. So by using the circuit, let's see the small analysis behind that. So in that op amp, in the feedback, usually we will connect the feedback resistor in the feedback path. Now here one BJT is connected in the feedback path. So emitter is connected with the output, collector is connected with the negative terminal of the op amp. Here we know that the VI relationship of the transistor for the that is become diode characteristics. It is given by IE, that is emitter current, that is equal to IS into exponential of QVE divided by KT minus 1, equation number 1. Here IC and IE equal to IC equal to IE for grounded based in transistor. So when that time collector current, that is equal to IS into the exponential of QVE divided by KT minus 1, equation number 2, where IS is the emitter saturation current in the range of 10 power minus 3 ampere, K is the Boltzmann constant, T is the absolute temperature in degree Kelvin. From the equation number 2, we are having IC by IS ratio, that is equal to exponential QVE divided by KT minus 1. So in that some approximation is assumed here. IC by IS is greater than 1. So by the way, IC greater than IS equal to 10 power minus 3 minus 13 ampere. By taking the natural log on both sides in the above equation, we will get emitter voltage, that is equation number 3. Emitter voltage, that is equal to KT by Q ln of IC by IS, equation number 3. So from the circuit, we know that collector current, that is equal to VI by R1, equation number 4. By the way, emitter voltage, that is equal to minus R0, this is equation number 5. By substituting 4 and 5 in equation number 3, we are getting the output voltage minus KT divided by Q ln of input voltage divided by reference voltage. So the disadvantage in logarithmic amplifier is the circuit has the problem with saturation current. Hence it may be vary from one transistor with the temperature. Hence a stable reference voltage cannot be maintained. To avoid this, logarithmic amplifier, the basic circuit is modified. So this is the modified circuit, logarithmic amplifier circuit with IS and temperature varying condition with the compensation. So by using that circuit, we are doing the analysis here. So IS1, IS2, that is equal to consider as IS. So V1 can be written as minus KT by Q ln of VI minus R1 IS. V2 can be minus KT by Q ln of reference voltage divided by R1 IS. Output voltage, that is equal to V2 minus V1. So V0 equal to the subtraction from V2 minus V1. Finally, we are getting KT by Q ln of VI divided by reference voltage. Still, V0 is depend on capital T, that is the temperature. Hence, the amplifier 4 will not compensate this problem. Amplifier 4 provides a non-inverting gain. The closed loop gain, we know that 1 plus RF by R1 from the voltage gain, that is equal to 1 plus R2 by RTC. The RTC is the temperature sensitive resistance with the positive coefficient temperature. It is called sensistor. So by the way, the overall output, compensated output voltage, that is equal to voltage gain into V0. So 1 plus R2 divided by RTC, KT by Q ln of VI divided by reference voltage. So in the above modified circuit we have used 4 op amp. So that is one more disadvantage. In order to give the solution to that, we are having one more remedy by using 2 op amp. So FET based op amp can also be used. So this is the other modified circuit, other method. So next, anti-lag amplifier. Here basic and logarithmic circuit is connected in parallel manner. So finally the output temperature in the output side, temperature compensation resistor also connected in the one point of the output voltage. Here input voltage is depend on R2 on the temperature compensating voltage network. Next, the output voltage is basically negative, and emitter base voltage of transistor 1 is given in the equation number 1. By the way, for transistor 2 it is given in equation number 2. Now the emitter base voltage of transistor 2 will be right in the equation 3. After that, the voltage at the point A, it is equation number 4, minus kT by q ln of V0 by I R1 Is. So after that, base voltage of transistor 2, that is equal to RTC divided by R2 plus RTC into VA. It is equation number 5. So by doing the analysis, substitute the third and fifth equation in this equation. So the overall emitter voltage of the transistor 2 will be the sum of base voltage of transistor 2 plus emitter base voltage of transistor 2. So if we are applying that, we are getting equation number 6. So after that, by equating fourth equation and the sixth equation, we are getting this equation. So after doing some approximation and simplification, finally we are getting this equation. So final log 10 A, that is equal to 0.433 ln of A, by taking on both sides the above equation. So by doing the simplification, here we are getting the equation as V0 equal to reference voltage into 10 power minus K dash into Vi. So K dash will be considered like this. So final logarithmic output voltage is this one.